Hello, everybody. Today I'm going to talk about an article that's called an integrated self-driven microfluidic device for rapid detection of the influenza AH1N1 virus by reverse transcriptation loop-mediated isothermal amplification. The most common strategies to detect the influenza or for influenza diagnostic are virus culture, serological assays, rapid influenza diagnostic tests, or RTs, and polymerase chain reaction or PCR-based methods. Most of them are used for clinical applications. However, they have many constraints. For example, in the case of virus culture, it takes a lot of time and they require expensive and large-scale equipment. The same happens for the polymerase for the PCR-based methods. They require a lot of time. I mean, it's uh, less than the time required for virus culture, but in terms of point of care applications, it is about 2 or 3 hours. So it's not applicable in the field in point of care applications. Serological assays and rapid influenza diagnostic test uh, requires a lot of less time, require about 15-20 minutes, but they have higher limits of detection. They are about 10 to the 4 or 10 to 6 uh, limit of detection. So they have limited sensitivity that may lead to commonly false negative diagnosis. So in this case, to solve this problem, the authors developed a chip that is composed of two regions. So the objective with this chip is to perform virus isolation, virus lysis, RT-LAMP, and diagnosis all in the same chip using small amounts of sample and small amounts of reagents. Here we can see the image of the chip. It's composed by two zones, as I mentioned before. This is the first zone here. I'm just spotlighting here. Is the zone for the sample preparation, for the virus lysis, for the first RT-LAMP, and for the detection of influenza A in the sample, in a human sample. This is the second zone. It's used for the positive control and negative control. Here we can see the chip structure. It's composed of 4 layers. The bottom layer is a glass one. So the second layer is a hydrophobic PDMS layer without any design. The design and the hydrophilic covering of the PDMS of the second PDMS layer is achieved by using by using a hydrophilic UV cure glue that covers and that grabs the hydrophobic PDMS layer. We can see here that this hydrophilic film only covers the inputs or and the channels. We can see that it's not connected in many zones, but we will see later why that happens. And the last layer, the top layer of this chip, is the microfluidic structure layer, which contains the channels, the inputs, the outputs, and the design of the whole. We can see here a sketch where all the steps of the reaction happens. Here we can see that we have 4 inputs, one for the virus sample that could be human, one for the magnetic bits that are going to isolate the virus from any other materials, one for the wash buffer that in this case is deionized distilled water, one for the lysis buffer. that it's going to destroy all the particles that are not needed for the RT lamp. Here is the pre-treatment area. We can see here that first of all, virus enters virus samples and magnetic beads. These we see are hydrophobic valves. We can see here a two-way valve, one-way valve, two-way valves, and we're going to see how that works to carry out the assays. First, virus sample and magnetic beads enters the pretreatment area. After the samples are taken by the magnetic beads, we wash the sample and all the material that is not needed goes to the waste chamber. After this material is washed, the lysis buffer comes to the pretreatment area and it performs lysis. So we can only have um, viral RNA in this case, and the other things that are not required for this assay goes to the waste chamber. Here we dilute the RNA extracted from the virus and comes for another pond. Here it mixes with the diluted genetic material, mixes with RT-LAM reagent. After that, we mix this reagent and viral material, the amplified genetic material with mineral oil. So we prevent the evaporation of the samples. And here we will see a change in color, a colorimetric assay. Same happens for positive control and for negative control. The only difference is that for positive control, the input is AH1N1 viral RNA, pure, and for the negative control, the input is deionized distilled water. Here we can see how the valves are, the mechanism of hydrophobic valves that are located in many of the unions of the joints. Here we can see these are the channels, and the valves are have a greater width and a greater height compared to the hydrophilic channels. We're going to see how those work later. This is the mechanism, the principle of action, and schematic illustration of the experimental procedure. Here is the loading of viral particles with the magnetic beads. Those magnetic beads are attached with aptamers that are going to recognize the viral particles and cause them to be captured. So here in this scheme, these are the magnetic beads and the virus attached to them. After that, we use a magnet, so only the attached viruses with magnetic beads stay in our pre-treatment zone. All the attached particles are going to be washed. After we attached the viruses, we wash them, and here in this step, we add the lysis buffer, so we only get single-stranded RNA from the influenza A virus. This could be applied for other viruses, but this specific application here in this article is for influenza A. After that, it goes to the other chamber, to the other treatment chamber, where RT lamp is gonna happen. It happens at a reaction at the temperature above 60 Celsius degrees, And after that, we are going to have, after an incubation time, we are going to have amplified material, amplified genetic material. Once we have amplified RNA, we go to the step of colorimetric assay. This happens if we come here. This happens in this zone, in this region, that it's called the detection area. We are going to see a change in color when the samples are positive, and we are going to see not changing color from purple to nothing when the samples are negative. Here we can see the working principle of the hydrophobic valves that I mentioned before. So these valves are designed in a manner that they do not allow the pass. They do not allow liquids passing from inputs to the pretreatment and to the detection areas or reaction areas. So here we can see the valve closed, naturally closed, normally it's closed, and it only opens when they are actuated with external vibrations. So here we can see with external forces. Here we can see the actuation. It only uses a tip. We can use a pipette tip. So the the liquids can flow to the pretreatment area. But here we have one problem when only they are allowed to pass. Because the volumes are very low, we will have a laminar flow that it's observed here in the image figure in the image F. Here we have that these are not mixed. We are looking for them to be completely mixed. So we use this system. They use the system. A pipette tip attached to a vibration motor. So we have not only the actuation of the valves, but only a vibration force that that causes a chaotic flow and cause the liquids to be mixed. So it's only placed here with the vibration for 1 second, and we will have the, the liquids accurately mixed. Here we have the loading chambers. It's the flow path. It's from the loading chambers to the pretreatment area and then to the waste chamber. The waste chamber is covered with filter paper or an absorbent pad. So here we have that when the actuation, when the hydrophobic valves located here, the two-way valve and a one-way valve, when they are actuated, the capillary pressure is negative, so they can flow easily and freely to the required areas. For the colorimetric assays, H and B was used as the colorimetric indicator that was previously described in this article. It is added to the master mix of the RT-LAMP reaction. So we are going to see how the colorimetric assay happens. When we have a negative sample or a negative control, we will observe a purple color. When the sample is positive, we will see a change in the color to sky blue. The intensity of the color change will depends on the concentration that our sample has. We will see that this has a very this method is very specific and very sensitive. In this figure, we can see that it's very specific. Here we have the negative control, an influenza B sample, influenza A H3N2 sample, enterococcus bacterial sample, and E. coli bacterial sample. And of course, we have our target, it's influenza A H1N1. Here we can see that all samples get the same color, purple, except for influenza A H1N1 sample, which has uh, a blue color. It is compared with electrophoresis samples, with an electrophoresis assay, and here we have that only influenza A H1N1 has amplified material. So it confirms the specificity of this assay using a lab-on-a-chip approach. To detect or to assess the limit of the detection, they perform the same assay but with serial dilutions from 10 to the 7 to 10 to the minus 1. We have our negative sample that is purple, of course. We have concentrations from 10 to the 7th to 10 to the minus 1. And here we have that only uh, concentrations of 10 to the 0 and 10 to the minus 1 has a purple color, indicating that these are not detected. Uh, this assay, this approach, does not detect concentrations from concentrations lower than 10 to the 1 copies. It is compared with the electrophoresis assay. Here we have same results as before. So it has very high specificity and very low limit of detection. Finally, we have a full assay carried out in the chip, in the stated chip, in the proposed chip. Here we have the inputs, the pretreatment tone, and here we have the first RT lamp performed. So we can see that the positive samples look sky blue, have a sky blue color, as well as the positive control, and our negative control stays purple. Here we have another say to confirm the limit of the proposed limit of detection, but now it is measured in terms of hemagglutinating units. So in this case, the limit of detection for hemagglutinating units is about 3.2 times 10 to the minus 4 hemagglutinating units. It was evaluated using concentrations from 3.2 times 10 to the 1 until 3.2 times 10 to the minus 5. Here we can see that only the change in color is observed only until 3.2 times 10 to the minus 4, and lower of them, the samples are not detected. As conclusions, the author stated that the samples and reagents could be transported by capillary action and hydrophobic sub-valve that we observed before how this works. Emanate from a pipette tip connected to a vibration-generating motor, the valve actuation was capable of mixing to egrified completion within 1 second. This is very important because without this vibration, the samples will not mix readily. They stay separated as it's happening a laminar flow in the pretreatment area. So it's very important to use this vibration bar. Also, the sample pretreatment, virus lysis, RT lamp, and colorimetric development steps all were performed on chip within 4 minutes. This represents a huge step uh, for uh, for point of care applications because when compared with RT-PCR based methods, it reduces the time from 2 hours to only 4 minutes. When we compare this method with the RIDT methods, it has a higher value, higher time, but the limit of detection is very, very low. It's lower than RIDT's approaches. because in this case, in this chip application, the limit of detection was only 87 copies of the H1N1 virus. Also, this chip can be modified so the entire manual progress could be automatically controlled while replaced with a microcontroller. So we can use Arduino approaches, Raspberry Pi approaches to get an automatic process for this application. Also, the cost of the developed disposable device and reagents were estimated to be $3 for each assay, when compared to currently commercial available ITTs, which cost 10 to 45 to $24.5. The price of this the price of this developed device is much more competitive. Thus, this microfluidic device could therefore serve as a promising portable device for point-of-care influenza diagnostics.